Did you guys hear about the meteorologist in North Dakota? Oh. Huh? So a meteorologist walks into a bar.
It sounded like
No. Apparently he got into some serious trouble because he had just gone on the air and had some sort of anxiety attack or something like that. I'm only saying this because I didn't record it. But so he started it with 2 swear words and another inappropriate term, let's say. So if you get a chance, look up meteorologist North Dakota on YouTube. It's an unfortunate way for him to start his career. He actually has this right after that. Anyway. Okay, so far we've talked about numerical methods for horizontal discretizations. We've talked about numerical methods for temporal discretizations. And so today we're going to turn our attention towards the next of the three major components in atmospheric models, and that's going to be the vertical. And the vertical has to be treated significantly differently than the horizontal, just because it has some very unique characteristics associated with it. So with regards to course projects, just a reminder, 42 days until course project presentations. I hope you guys are sufficiently stressed. No, seriously though, if you have any questions or need assistance or something like that, please email me. Make sure that you have an outline of it, exactly the steps that you need in order to complete the course project. Yeah, just let me know. So the outline for today's talk, unique aspects of the vertical coordinate, what makes it so special, overview of vertical coordinate systems. This is where I end up with slides and slides full of equations. You can review those later, commit them to memory if desired. Terrain following variations, so what we have to do in order to take into account the fact that our bottom boundary condition is actually variable in space. Vertical computational modes, some other issues that we need to account for in the vertical direction, and semi-Lagrangian layers. I want to acknowledge Michael Toy, who came up with a lot of the slides associated with this particular lecture, because he gave a similar lecture at the DCMIT workshop back in the summer. So, unique aspects of vertical. I know you've seen this slide 3 times roughly so far, but hopefully it can give you some idea of the fact that the vertical is just so significantly different than the horizontal in terms of its basic properties. So can you name some specific characteristics of the vertical that make it significantly different than the horizontal? You don't have to worry about your being recorded. This may be held against you later. Come on, throw it anything.
It changes a lot faster.
It changes a lot faster, yes. Temperature will change dramatically if you go up 10 kilometers. It goes to about -50 degrees Celsius. If you go 10 kilometers north of here, it does not go to -50 degrees Celsius, unfortunately. Anything else?
Pressure.
Pressure.
Yeah.
Pressure decays exponentially quickly with height. Anything else? Kind of associated with that, the length scales are different. In the horizontal, the length scale is about 100 kilometers, and the vertical, the length scale is about 100 meters in order to get a similar amount of variation. So these are all issues. There's one more thing that I'm looking for. Think back to forces. What forces might only be acting in the vertical direction?
Gravity.
Gravity, exactly. And gravity is something we need to take into account that does not appear in the horizontal equations of motion. So gravity acts in the vertical. If we look at the vertical momentum equation then, in terms of the typical scales associated with these terms, we have that the pressure gradient force in the vertical and the gravitational force roughly balance each other and are significantly larger than any of the other terms in this equation by a factor of 4 orders of magnitude. This means that to a large degree, the vertical in the atmosphere can be described as a balance between these 2 forces known as hydrostatic balance. So consequently, you end up with stratification of the atmosphere. If we were to consider an approximately isothermal layer of the atmosphere in hydrostatic balance, so we say that since these 2 terms are so much larger than the other terms, we're going to say, okay, they're approximately equal to 0, and this will give us the first order approximation to actually it'll be a fourth order approximation of what's going on in the vertical direction. We combine that with the ideal gas law with a constant temperature profile and substitute it in here for density in order to eliminate density from the equation. We end up with a differential equation here where the only dependent variable is the pressure P. So we can solve that differential equation then for P as a function of radius, and we obtain something that looks like this. The pressure is equal to P naught, which is a reference pressure, times an exponent to the minus Gz over Rd, which is the ideal gas constant for dry air, times the isothermal layer temperature. Here Z is defined as the altitude, which is simply the radius minus the radius of the Earth, A. So we have exponential decay then of both the pressure and density fields in the vertical direction, and consequently very rapid variation associated. If you go up over one scale height of the atmosphere, which is defined as Rd times T naught over G, then your pressure is going to drop by a factor of E, or about 2.8. Does anybody know roughly what the scale height of a dry atmosphere is?
Is it 8 kilometers?
It's about 8 kilometers. Does anybody know what the scale height of a moist atmosphere is?
8 kilometers.
8 kilometers, no. It's slightly shorter than that. So it's about 5 kilometers. So gradients are going to be much stronger in the vertical direction, as were mentioned earlier. It's going to be much colder 10 kilometers straight up. It goes down to about minus 50 degrees Celsius. And it's much harder to breathe further up because we have this dramatic drop in atmospheric pressure. And both of these characteristics are significantly different than 10 kilometers down the road. In addition, we have to deal with boundary conditions of the vertical, which are not in the horizontal direction. Remember, we're doing global modeling, so there's no such thing as lateral boundary conditions in this case, because everything just kind of flows around in a periodic manner. But in the vertical, we have boundary conditions. At the surface, we say no flow, which basically means that you don't have air which is allowed to go into the surface. So no flow perpendicular to the plane which defines the surface layer. And at the top of the atmosphere, we say that the pressure goes to 0. So as height goes to infinity, the pressure of the atmosphere goes to 0. In addition, we have many distinct physical processes associated with the vertical coordinate. Convection, boundary layer, namely we need to have some representation of viscous processes which occur near the surface, where the viscosity term actually becomes important. Radiation, if we're having solar radiation coming from above, it's represented via short wavelength radiation coming to the surface, and emissions from the surface are long wave radiation going back up through the atmosphere. These are all approximated to be occurring within a single vertical layer in most atmospheric models. Waves, we need to worry about troposphere-stratosphere interaction. In order to learn more about that, you can talk with Harry Newman. He is a master of this subject. As well, there's some not-so-physical processes, which include things like a model top sponge layer. That is, near the model top, we typically add some numerical viscosity in order to prevent waves from bouncing back from the top. The idea here being that if we don't put this sponge layer in, the top of the atmosphere is treated as a solid surface, and you can imagine that if you perturb the fluid as it goes towards that solid surface, you're going to get wave reflection associated with it. So the existence of this sponge layer, which is something I'm going to discuss when we get to the diffusion section of the class, is used in order to basically remove those waves and treat them as if they're propagating freely up towards infinity. With regards to numerical considerations of what we need to take into account, we have a choice of vertical coordinate system. So this can be thought of somewhat analogous to, in the horizontal, we have the choice of a regular latitude, longitude grid. We have a choice of a cubed sphere grid. We have a choice of an icosahedral grid, or all those other options. Here, the choice of coordinate system will play directly into the equations of motion, and some of them are going to be better suited for atmospheric models than others. Some of the more popular ones include height coordinates, so that's using just the altitude as a vertical coordinate. Pressure coordinates, which use the atmospheric pressure, which will decay with height typically. as a vertical coordinate. Isentropic coordinates, we're going to use the potential temperature as a coordinate surface. So this one's closely related to adiabatic flow in the atmosphere. If you have adiabatic flow in the atmosphere, that means all of your isotropes will stay constant over time. And you will not have any exchange between isotropic layers. We can use a mass coordinate, which is basically you integrate the amount of mass above you at any given point, and that gives you your. As you can imagine, that is also one which is monotone. As you get higher in the atmosphere, the amount of mass above you is strictly decreasing. And with regards to terrain, we need to choose whether we're using terrain following coordinates or maybe cut cell coordinates. We need to ensure that the hydrostatic relation is satisfied for a stratified atmosphere. That is, we need to make sure that that huge balance that I discussed earlier with the vertical momentum equation is sustained. We need to determine if we're staggering variables. I mean, this is the same problem that I discussed earlier with the Arakawa grids. Remember, with the A grid, you end up with strange 2 delta X imprinting because of the way that the finite difference operator is taken. We have that same problem in the vertical if we don't do our staggering properly. And how to handle the boundary conditions. So, the set of numerical considerations for the vertical is, I would say, even more significant than for the horizontal direction. And that's why, in practice, when people are designing these atmospheric models, there's usually a hierarchy associated with it. Namely, they start with very simple, shallow water equations in 1D. Then they don't have to worry about using a vertical coordinate because there's only one vertical layer in a shallow water equation set. Only when you know that you can do the shallow water equations properly, then you can extend it in order to add more layers in the vertical via an appropriate new vertical numerical scheme. Inevitably, the choice of your vertical scheme can be completely independent of the choice of your horizontal scheme. And in a lot of models, including the CAM model, they recently just took out their previous vertical scheme and just put in a new vertical scheme without changing anything with regards to how the horizontal coordinate is handled. So let's look back at the equations of motion. So the non-hydrostatic primitive equations, we derived these previously for height coordinates. They look like this. We have 2 equations governing the horizontal momentum. We have a vertical momentum equation. I should probably note this is under the shallow atmosphere approximation. So with the shallow atmosphere approximation, I've dropped all the cosine Coriolis terms. I've dropped the viscous term here on the right-hand side, and some of the additional curvature terms that are shown up. We have the continuity equation, which is associated with conservation of mass. We have the thermodynamic equation here, which allows us to link temperature, pressure, and density together via a prognostic equation. The capital D derivatives here are all material derivatives, which means that if we were to expand them out, we would have a partial derivative with respect to time. We have a horizontal component of the divergence. So this is UH here representing the horizontal velocity vector, so just U and V, dotted with a gradient along constant z surfaces. So that's ddx comma ddy as the vector. And then finally we have the vertical component, which is w times ddz, or partial z. And the reason that these two are typically separated are for the same reason that we're treating a vertical coordinate different than the horizontal coordinate. They have different properties associated with them, so in practice it's better to separate these and treat them separately. If we were to consider the hydrostatic primitive equations, we lose one of the prognostic equations that I just talked about, and it gets replaced with a diagnostic equation. Basically, we take that vertical momentum equation that we had previously, and we replace it with something which simply represents hydrostatic balance. This is a good approximation. Thoughts?
On large scale.
On large scales, yes. Would you use this for global model? Would you use it when running WRF?
When it gets past 10 km or lower than
Yeah, it's the cutting point's at about 10 kilometers. So larger than 10 kilometers horizontal scale, it turns out that this is a good approximation. Kind of interesting, actually, that the horizontal scale actually determines whether the hydrostatic approximation works or not. Anyway, so in the hydrostatic case, then we have this equation which basically says it tells us how pressure and density are related to one another in the vertical. But if you notice, we don't have any equation here specifically for W. W does not evolve on its own, hence it's not a diagnostic quantity. Or sorry, it's not a prognostic quantity. It is a diagnostic quantity, which means we need to extract what W is from how the other variables in the system behave. And in Z coordinates, non-hydrostatic looks pretty straightforward. Things are very easy. In order to get W and Z coordinates, we actually use the thermodynamic equation, expand it using the material derivative, and then solve it for W. We can just integrate that from the bottom of the atmosphere to a particular coordinate in Z. And it follows this simple relationship right here. There's a combination of terms. This is J here, this is the diabatic heating. T is the temperature. B and Q are defined via these very simple expressions here. Yeah, so fairly straightforward, and this is implemented all the time in atmospheric models. No, that's a lie. Nobody ever implements this. This is horrible. This is really awful. Nobody would ever do this. This is why Z coordinates are never used in hydrostatic models. Because you can just imagine how many numerical errors you would make trying to discretize this, let alone errors just trying to write the code in order to compute this. But nonetheless, this is a mess. Z coordinates do work very well for non-hydrostatic models, because then it's just this simple relationship right here. W is prognosed. So this is a major motivation then for why we would choose different coordinates associated with the model. So in order to switch from Z coordinates to some other arbitrary coordinate surface, so let's say we have an eta coordinate which has vertical coordinate lines given by these red lines, and correspondingly we have Z coordinate lines given by these straight lines, we have to have a transformation rule which allows us to transform derivatives along constant Z surfaces into derivatives along constant eta surfaces. So here eta can be anything. We can choose eta to be pressure, we can choose eta to be isotropes, etc., etc. Let's see here. In order to give you some basic idea of how these transformation rules are extracted, consider the following. We have some coordinate surface here. So this is going to be a line of constant eta. This is a line of constant Z. We're interested in taking a derivative along a line of constant eta here. So we're going to say this is going to be Q1, this is going to be Q2, and this is going to be Q3. Okay. So Q3 minus Q1 divided by delta x. So this is delta x here. This is a Z constant surface. This is eta constant. Like so. Q3 minus Q1 divided by delta x. Is going to be equal to Q3 minus Q2 over delta x minus Q plus Q2 minus Q1 all over delta x. Do you guys see that those two are equivalent to one another? So this Q3 minus Q1 over delta x, that represents what's approximately a derivative of Q along a surface of constant eta. So it's this difference along eta constant. Q3 minus Q2, this is going to be equal to, let's write it as Q3 minus Q2 divided by delta Z times delta Z over delta x. So just add a factor of 1 into that expression, plus Q2 minus Q1. So Q2 minus Q1 is going to be approximately equal to di Q, di x along the surface of constant Z. Right? This difference is just being taken along the surface of constant Z. So Q2 minus Q1 over delta x. And this Q3 minus Q2 then, this is going to be the change in Q times the change in Z times delta Z over delta x plus Q2 minus Q1 over delta x. Okay, so let's see here. If we're to, so this delta Z over delta x here, this is going to be the change in Z, the Z coordinate following along a line of constant eta. So this one's approximately equal to di Z, di x along the surface of constant eta, and this di Q di Z then can be written as di Q di eta times di eta di Z, just via chain rule. So consequently you end up with an expression that basically says if you have any arbitrary derivative along a surface of constant Z, in terms of derivatives along surfaces of constant eta then, this is the derivative of x along the surface of constant eta minus the derivative of the Z coordinate with respect to x along that surface eta, so it's basically this difference right here, delta Z, times di eta di Z, and then times di eta. And that's exactly that first expression right there. Okay? So this is our transformation rule for then changing the derivatives from the equations of motion that we had previously. All of these pressure derivative terms here need to be transformed to be derivatives along surfaces of constant eta from derivatives of constant, derivatives along surfaces of constant Z. And in addition, we also have to introduce a new generalized vertical velocity, which basically represents how the eta coordinate is changing following a fluid parcel. So this is the analog of the material derivative in these eta coordinates. And it's simply going to be given by the change in eta with respect to time along constant Z surface. This is just the localized change in eta with respect to t, plus the horizontal velocity dotted with the gradient of eta along constant Z surface, and then plus W times di eta di Z. Basically what this means is that if you have a fluid parcel that's moving through space, its eta value is going to change as you move through space. And however its eta value changes, its rate of change is given, it then gives this generalized concept of velocity. If eta was simply, if we simply use the regular height coordinate Z associated with this expression, then eta dot would be Z dot, this would be dz dt. The derivative of Z with respect to time along constant Z surface is going to be 0. The derivative of Z, or the derivative with respect to Z of eta along a constant, so along a constant Z surface, if you differentiate a constant Z value, this is going to give 0. Derivative of Z with respect to Z is 1. There you go. It's not 0. And so you just get W. And so in the height coordinates, then you recover exactly what you would expect. So this is our general coordinate transform. You can now say, yay, I have the power to define vertical coordinates however the heck I want. I'm going to define a vertical coordinate that uses pressure as a variable. Ha, take that. So you can't really choose anything though. You have to note that the quantity has to be monotone. So it needs to be either strictly increasing or decreasing as a function of height. So you can't choose temperature, for instance, because temperature decreases initially in the atmosphere, then it increases for a bit, then it decreases. It's not a unique coordinate. You can't say specifically, for a given value of temperature, this is the corresponding height in the atmosphere. It turns out that that's typically the case for pressure, that we're allowed to do that. For the mass coordinate, we're allowed to do that. For isotropes, we're not always allowed to do that. We have to be very careful. But in general, we can. So with the non-hydrostatic equations then, we have, in general coordinates, so this is a general coordinate system, we have 6 prognostic equations, 1 constraint equation. We just made our lives a lot more difficult because these equations suddenly look a lot messier than before. We have a new mass variable, m, which is going to be defined by rho times the derivative of z with respect to this eta coordinate. So it's known as the pseudo-density. It's closely related to a thickness variable. We have our typical material derivative, ideal gas laws as usual. This is a new form of the continuity equation, which defines this mass variable as it floats around in space. It's here. Anything else interesting you can see about these equations? What about the pressure gradient? Something looks strange about the pressure gradient? No, pressure gradient looks completely normal. It has 2 terms though. Both these terms here represent the pressure gradient. That's kind of strange, I would say. Strange enough that I pointed it out on the slide. So these are 2 terms associated with the pressure gradient. This might be problematic actually when we consider numerical discretization, because that means that if both these terms are about the same magnitude but different signs, then we're trying to take the difference between 2 terms which are roughly equal but different, and consequently you're going to get numerical errors associated with that. There are 2 choices of eta that will reduce this to a 1-term pressure gradient. Can you name one of the 2? How would this pressure gradient be reduced to 1 term?
Pressure coordinate?
Pressure coordinates. Why?
Oh, well, I actually didn't think about it too much.
No, it's the right answer. But
Well, I know one of the partials, down over there dropped the,
this one?
forget it.
Say yes. What's the derivative of pressure with respect to longitude along a surface of constant pressure? 0. Exactly. Both of these terms would drop under pressure coordinates because they're derivatives of pressure along surfaces where pressure is constant. What's the other coordinate system where we get 1-term pressure gradient? Hint, you've seen it before. Z, yes. In Z coordinates, this term does not drop. This is actually the exact same pressure term that we usually see in Z coordinates. But over here on the right-hand side, the derivative of Z with respect to longitude along a surface of constant Z is 0. So this term would then drop in that case. Those are the only 2 choices of vertical coordinate systems which allows us to actually retain a 1-term horizontal pressure gradient for us and avoid those nasty issues associated with the numerics. It turns out that the Z value actually becomes predicted in general coordinates. This is analogous to geopotential height, essentially. If we have an equation which predicts geopotential height, or geopotential, then it's analogous to predicting the Z value. So in pressure coordinates, if we choose eta equals P, then we end up with this generalized notion of vertical coordinate, which is omega, and it's given by the change in pressure following a fluid parcel. In the non-hydrostatic equations, the vertical momentum equation from here, if eta is P, then di P is equal to 1, and so the vertical momentum equation simply reduces to dw dt equals minus 1 over m minus g. The horizontal pressure gradient looks like this, 1 over m times the gradient of z. This is analogous to the gradient of the geopotential. And the continuity equation looks like this. The problem is the vertical velocity is actually really difficult to diagnose from this system, again. But in the hydrostatic case, life's really easy. Here, in the hydrostatic case, we drop this dw dt, and so this is equal to 0, and since g is a constant, we just get that the pseudo-density m is equal to minus 1 over g. So the pseudo-density is actually constant. That basically says that the layer thickness contains the same amount of mass regardless of where you are in the atmosphere. There's a single term pressure gradient, it's really nice, and diagnostic continuity equation. In this case, in the continuity equation here, if m is constant, this term is 0. All these m's fall out of the equation. We divide through by m, and we get something which looks like this. So that means in order to diagnose the vertical velocity omega here, we just have to integrate this continuity equation from the top of the atmosphere at p equals 0 to some pressure surface over the horizontal divergence of the velocity. So this is much nicer than with z coordinates, right? So the interesting thing is, height coordinates work really well with non-hydrostatic equations. Pressure coordinates work really well with hydrostatic equations. We can also define something known as a mass coordinate. This was originally proposed by Laprice in 1992. Basically, we're just going to say the coordinate is going to be the amount of mass above us at any given point. And it turns out that in the hydrostatic case, this is exactly the pressure. So consequently, for mass coordinates, you end up with hydrostatic equations which are identical to the pressure equations, but the bonus is, with mass coordinates, the non-hydrostatic equations also lead to a pseudo-density, which is constant. The horizontal pressure gradient ends up being 2 terms, so you need to worry about that. And the continuity equation is, again, its simple form here. So pi dot is going to be that generalized vertical velocity. We're going to integrate that over 0 to pi, where pi is this quantity of mass above us. And we obtain a diagnostic vertical velocity in both the hydrostatic and non-hydrostatic cases. For isentropic coordinates, or adiabatic coordinates, we can choose A equals theta, or the potential temperature, where potential temperature is defined via this expression here. Basically, it arises from the thermodynamic equation, reducing to, in the case of adiabatic flow, so no extra heating added to the system, we observe that this quantity theta is actually preserved following fluid process. That's from atmospheric dynamics, if you remember back. So then the vertical velocity is going to be proportional to the diabatic heating, because we know that this d theta dt, in the case of adiabatic flow, it's equal to 0. So there's no vertical exchange, there's no notion of this generalized vertical velocity in the adiabatic case. But if, in case there is diabatic heating, in case this capital J is non-zero, then there will be an induced vertical velocity. So the important bit here is that in an adiabatic atmosphere, the vertical motion is 0. So in this adiabatic case then, with isentropic coordinates, you get 0 exchange between model levels. So this is consistent with the physics of the system. So consequently, in our numerical simulation, if we were interested in having a tracer that was confined to a single isentropic layer with adiabatic heating, with this coordinate system we could guarantee that the tracer would stay in that single layer. So this minimizes errors then associated with vertical advection. The issue is, as I mentioned earlier, this is what this is what isentropes look like for a breaking mountain wave. Namely, you have a low potential temperature down here and an increasing potential temperature with height over this layer. Issues? Analogous to the problem that we had with temperature earlier, isentropes are not monotone with height. You can look at even a cross-section right here, you notice it's increasing, 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 then right here it decreases, and then it increases, 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 and maybe decreases around here, and then increases a bit. Whenever you have this non-monotonicity, so it's not constantly increasing or it's not constantly decreasing, then your choice of variable no longer works as a vertical coordinate. And so you have to fix that. This is usually done by hybridizing the coordinate. That is, you say, okay, part of the coordinate is going to come from isotropes, part of it's going to come from like a height coordinate or something. So it's something you need to be careful with. Some isotropic coordinates are not used in any operational atmospheric model right now because of this problem. It's very difficult to deal with this. However, there do exist experimental versions of CAM which do implement an isotropic coordinate, and they've been able to show that the isotropic coordinate does improve model results because it has that nice adiabatic property. So a summary of the 4 vertical coordinates that we discussed. Height coordinate is suitable for non-hydrostatic models, but not preferred for hydrostatic models, as it's a complete mess in order to diagnose the vertical velocity. Pressure is not preferred for non-hydrostatic models because it's very difficult to obtain omega, but it's really good for hydrostatic models. Mass works in both, and potential temperature works in both, although there's some challenges in the non-hydrostatic case associated with that non-monotonicity of the coordinate. So going forward, a lot of the next generation of models are either using a height coordinate and implementing it as a purely non-hydrostatic model, or they're using a Laprise-based mass coordinate in order to allow for both hydrostatic and non-hydrostatic options. Now the next issue that we have to worry about is the presence of topography. And here there's another set of options that we have with regards to how we can choose the handling of topography in the model. Here are 3 common options taken from Alistair Adcroft's 1997 paper where he actually did this for an ocean model. We have step topography. We can just say, okay, if our topography is this dotted line right here, then we're just going to say if a cell is more than 50% covered by the topography, then that cell is considered to be a whole topography. It's going to be a solid wall here, solid wall on the bottom, solid wall on the side. We can use sigma coordinates or terrain following coordinates where we actually stretch our vertical coordinate surfaces in order to follow the topography. That's very commonly used in global atmospheric models. Or we can do shaved cells where we do a better job of representing the topography than the step case by saying, okay, we have a bunch of cells, we're going to ignore the fact that the topography is there, but we're going to shave off parts of those cells depending on which part is actually covered by the topography. So these are the 3 main options that we have really for representing topography. Choosing a bad option typically leads to a significant amount of model noise. And that's very apparent if you ever see a model run that's the step topography model. This representation of topography is just too coarse. These corners cause a lot of problems in the fluid flow equations. If you run a simulation over a mountain which is supposed to generate a smooth mountain response, you end up getting something which looks like this. Really nasty 2 delta x and 2 delta z type noise associated with the step topography model. The advantage of this thing is, of course, that you don't have to deal with small cells like you would in the shaved cell model, and it's an accurate representation of the horizontal pressure gradient force, which I'll get to momentarily. The disadvantage is poor representation of underlying topography and hard corners. It creates a lot of really unwanted noise. Shaved cells, I'm going to go ACB in this case. With a shaved cell, we can again compute the pressure gradient force along surfaces of constant z. Recall from earlier, with regards to this pressure gradient force comment, recall from earlier that the only 2 coordinate systems that allow for a single term pressure gradient force are height coordinates and pressure coordinates. If we introduce any sort of modification to that coordinate in order to make it follow the topography properly, that's going to lead to a 2-term pressure gradient force, and it will cause issues for actually computing that horizontal pressure gradient. So that's what I mean when I mention the accurate treatment of the pressure gradient force. The advantage of the shaved cell method is it allows for accurate treatment of topography. So we can actually shape these cells however we want. We can use second order methods, third order methods, fourth order, whatever. The disadvantage is small grid cells can affect the maximum time step size. Remember the CFL condition earlier. The maximum time step we can choose is proportional to the smallest cell in the domain. Look at this cell right here. This one's less than half the size of the original cell. It will be the cell then that determines the time step associated with the model, because we just shaved part of it off. You can imagine how bad it would get if we shaved off even more of it and made the cell really, really tiny. Then suddenly we're running this simulation where there's one cell which is causing us to use a really, really small time step. So this is an advantage, or this is a disadvantage that has yet to really be overcome. There are models that do use shaved cells though. The ocean land atmosphere model from the University of Miami, previously from Duke University, does use shaved cells. Sigma coordinates. This is the one which is dominantly used in atmospheric models today, global atmospheric models today. The issue with this is if you get down below, say, 5 kilometer resolution, suddenly the roughness of the topography is going to be generating a lot of random noise associated with the system. However, in this case, the topography is absorbed into the evolution equations, so we don't have to worry about any other boundary considerations. It's very accurate for smooth topography. We can make this underlying topography be any order that we want, and there's no added complications with it, essentially. The disadvantage is there's poor representation of the horizontal pressure gradient force near steep topography. If we have a pressure gradient force, here taken as a derivative of the z-coordinate along a surface of constant pressure, if this is equal to 0, in the base case, that is, we have a stable stratified atmosphere where the pressure is only a function of height, and height is only a function of pressure. This separates into two terms because of the two-term pressure gradient force. But these two terms don't necessarily cancel. We have to do a lot of numerical acrobatics in order to make sure that these two terms are actually able to cancel each other. And so that becomes problematic. We can change how the layers are represented with respect to height. We can use a Phillips sigma coordinate model. So this was introduced in 1957. You have the sigma coordinate, which is simply defined as pressure divided by pressure of the surface. Since the surface pressure changes depending on the topography, this introduces a new coordinate. So this is like our new value of eta that we plug into the coordinate transform equations that I showed you earlier. And it ends up looking something like this. At sigma equals 1, we have a coordinate line which follows the surface. And as you go to sigma equals 0, then that's a straight line at a fixed atmospheric height. So Galchen and Somerville, 1975, introduced something analogous. Skamrock and Klemp in 2008 in the Whorf model. So this is from the Whorf model. They used a mass-based vertical coordinate. You have normalized hydrostatic pressure, vertical. Simons and Burridge, 1981, introduced a hybrid coordinate. Basically, they said, why do we want the flat coordinate surface to be at the very top of the model? Why not make it closer down to the surface? Then we can take advantage of the fact that the pressure gradient force is calculated very accurately in this region. So they have this hybrid coordinate. It gets a bit more complicated. Shar, in 2002, introduced an even more complicated hybrid coordinate, which used like a two-layer smoothing of topography. And then you end up with something which has very sharp, jagged edges that match the topography at the lowest levels of the atmosphere, but those get smoothed out as you get higher up. And then eventually it goes towards something which looks more like Simons and Burridge. The choice of this underlying topography has important considerations for the type of numerical results that you get out of your dynamical core. With just a sigma coordinate model, we're going to take this bell-shaped tracer field and just move it over top of the mountain range, just using a second order advection scheme, so it's basically as simple as we can get. With a sigma coordinate, you get an incredible amount of noise associated with the fact that the tracer field keeps transitioning between different layers. And then when it comes out, it's highly deformed. With Simons and Burridge, the hybrid coordinate, the smooth coordinate lines end up somewhere around here, and so you get far less deformation associated with it. thing that they're hiding here is the fact that if you actually move this tracer field down in the atmosphere slightly, then you're going to get just as much noise as you do in the sigma coordinate system. And the SHAR model, they're basically flat coordinate lines at this point, so you can basically see no noise. So obviously SHAR, who wrote this paper in 2002, was like, look, our approach is the best. What they didn't mention is, of course, the fact that if you are infecting this thing very close to the topography down at the bottom, then you're going to have issues as well. The solution, I would claim, so take this with a grain of salt, is that you want to use a better infection scheme than a second order infection scheme in order to do this stuff properly. All right, so it is 4 p.m. So I will talk about vertical staggering briefly next time, and then finish up with a discussion of the choices that different atmospheric models have made. Any questions?
Yeah, with regard to the homework. So, you know, I'm receiving all the emails and stuff like that, kind of making me question what I had to include. Because I know there are basically two questions that are in the project description. There's basically describe the features of the wave,
Yeah.
and then the plots.
Yeah.
So, but it's almost like, are you asking us to do specific fields now? You want us to do more than, or?
No, I would just say that however you describe the evolution of the wave, you need to back it up with a corresponding figure.
Okay.
So if you want to say something like the wave causes mixing between warm temperatures and cold temperatures, then you want to show a plot of surface temperature showing how the wave transfers warm temperatures to the north and cold temperatures to the south.
Okay.
But you're basically given free rein in order to do whatever you want. Basically the idea is that you want to just explore the options that you have available to you and perhaps do something that would be relevant towards your course project.
And also, when you ask us to plot at day 9 specifically, does that mean all of day 9?
No, there's a specific output at day 9. That's array index number 36 in the output. The reason that I picked day 9, that's the one that's typically plotted for this baroclinic wave, because that's when the wave breaks. So that's when it transitions from a smooth wave to basically you get overturning associated with the wave and very rapid turbulent mixing. So that right at day 9, that's typically where you have that transition and where you have the most interesting, I suppose to some degree, effects on it. But you can plot later or you can plot earlier.
Okay.
If it helps you explain.
Oh yeah, it's more like trying to pinpoint exactly what time you wanted us to plot.
Yeah. So you can well, the vorticity plot script includes plots at day 8, 9, and 10. And so that's kind of like a prior to breaking